Hello everyone, myself TanujJhankal and I welcome you all in this third lecture of Multi-Level Inverter series. In this lecture, we will learn about different topologies of multi-level inverters, including conventional and some advanced ones. Okay, so before starting, as we have discussed in earlier lecture video of this series, that there are different types of multi-level inverters. Okay, and they are different levels: 3 level, 5 level, and 7 level. 9 level multi-level inverters we have seen in that video. Okay, now in this video lecture, we will see different type of topologies and their constructions and their switching states. Okay, so as the various topologies of multi-level inverters are reported in the literatures in so many years, the most commonly used multi-level inverter configurations are NPC, which are neutral point clamped or also known as diode clamped, and flying capacitor, which is also known as capacitor clamped, and cascaded H bridge, which is also known as cascaded multi-cell. Okay, so the comparative study have been carried out for these inverter topologies to judge their performances over time to time. The operating principle of these basic multi-level inverters configurations are discussed in various literatures and books which you can find on the online platforms. Okay, so let's start with the multi-level topologies. At the first topology is neutral point clamp multi-level inverter, or also known as NPC type multi-level inverter. Okay, in this class of multi-level inverter, the DC link is split into number of small voltage levels using a bank of series capacitor, uh, or we can say uh, using a number of series connected bulk capacitors. The inverter structure allows the connection of the inverter poles to any one of these voltage levels, thus generating multi-level voltage waveforms at the output. In year 1981, Nabi introduces a 3-level inverter, which is shown in the figure on the screen. The multi-level inverter, in this multi-level inverter, the midpoint O of two DC link capacitors C1 and C2 is defined as the neutral point. This multi-level inverter topology is popularly known as multi-level inverter topology or NPC type multi-level inverter topology or NPC type PWM inverter, as the midpoint voltage level is formed by clamping the switching diodes to the neutral point of the DC bus. Each leg of inverter consists of 4 switches and 2 diodes, which are known as clamping diodes. In this inverter, each pole of this inverter can attain one of the 3 voltage levels, which is minus VDC by 2, 0 and VDC by 2, with respect to the neutral point O. The output voltage at pole A of the inverter, which is VAO, reaches the level of VDC by 2 when the top switch S1 and S2 are turned on. When when we talk about the level minus VDC by 2, the switches S3 and S4 will be S13 and S14 will be on. Means these two bottom switches will be on for minus VDC by 2 and upper two switches will be on for plus VDC by 2. Okay, the voltage VAO gets clamped to neutral point through the diode D1 and D12, depending on the direction of load current. The inverter switches are switched in complementary fashion. For example, in pole A, when S11 is switched complementary to the S13, which means when S11 is on, the S13 will be off, and when S13 is on, the S11 will be off. Okay. Similarly, Similarly, S12 and S14 are complementary in nature, which means when S12 is working, S14 will be off, and when S14 is closed, S12 will be opened. Okay, means S12 and S14 will never operate at same time. The relation between the switch state and the pole voltage of any phase for any phase uh, can be summarized in the form of a table, something like this. Now, the key component that distinguish this circuit of a three-level inverter from a conventional two-level inverter are the clamping diodes. D11, D12 for A leg, D21 and D22 for B leg, D31 and D32 for leg C. Okay. The two diodes in each pole of the inverter uh, clamp the switch voltage to the half of the level of DC bus. Therefore, the maximum voltage stress on each switch is limited to the voltage across each capacitor, which is VDC by 2, when the capacitor voltage is assumed to be balanced or steady. Hence, the voltage stress of the inverter switch with these three level structure is half to that of conventional two level inverter that operates with the same DC link voltage VDC. It can be seen from the switching table that two switches of the pole are always open for any voltage level and thus share voltage stress equally. Thus, the voltage rating of the switch is half of the DC link voltage, and the blocking voltage rating of the clamped diode is also half of the DC link voltage. Now, in the extension of the three level inverter configuration to the higher number of levels is possible by subsequent splitting of DC bus. Okay. As simple generalized structure of multi-level inverter is presented in such, which is a direct realization of the multi-level concept using bidirectional switches, the DC link is split to several smaller voltage level and the output terminal can be connected to any of these levels by turning on the respective bidirectional switch. The stress on the different switch or different switches in this topology will depend on the position or on its position in the ladder structure, and the topmost and the bottommost switches have to block the full DC link voltages. A generalized structure of multi-level inverter proposed in is a direct extension of the NPC three-level inverter. Now the configuration for a five-level NPC structure is something like this. Okay, this is a five-level NPC structure where four series connected capacitors are used to release the 5 voltage levels. Each capacitor of a DC link have a voltage of VDC by 4 across it, and each switch have to block the voltage across one capacitor only. There are 4 pair of switches in each leg for from S11 to S15. Sorry, represented as S11, S12, S3, S13, S14, S15, S16, S17, and S18, which operates in complementary fashion, and thus the reverse blocking voltage rating of the power switch is equal to VDC by 4. The pole voltage can be equal to VDC by 2, VDC by 4, 0, minus VDC by 4, and minus VDC by 2 with respect to the neutral point O. Unlike the 3-level inverter or 3-level NPC inverter, the diode in the 5-level configuration have to be rated for different voltages, which can be higher than the blocking voltage of switching devices. The blocking voltage of each clamping diode depends on its position in the structure. And for the N-level inverter, the diode or the 2 diodes per leg will see like the first figure. Okay. Now, when the lower 3 devices, which are S16, S17, and S18 are on, diode D14 have to block 3 time capacitor voltage, that is 3 VDC by 4. Okay, and as evident in or as evident from figure. Similarly, D13 have to block 3 VDC by 4 voltage, while D12 and D15 have to block VDC by 2 voltage. Okay, whereas D11 and D16 in this figure have has to block only VDC by 4 voltage. Okay, and if you want to calculate the uh, voltage of diodes, you can calculate it by using a simple formula. Okay, and the formula is VD, which is diode voltage, is equals to VDC into n minus 1 minus k divided by n minus 1. Okay, so where in that formula, which is VD is equals to, or diode voltage is equals to VDC into n minus 1 minus k divided by n minus 1, the k is varying from 1 to n minus 2. Okay, now if you want to calculate the value of the voltage that a diode has to withstand, you can just place the number of n instead of n number of level of inverter, value of k, and just calculate the voltage level for that, or the voltage that diode has to withstand. Okay, or has to block. An extended structure for an n level inverter used a total of n minus 1 DC link capacitors. In general, for an NPC multi-level inverter topology, each capacitor has voltage across it equals to VDC divided by n minus 1. Okay, and the voltage stress on each switching device is equals to VDC divided by n minus 1, where n is the level of inverter. An n level inverter structure requires two n minus 1 switches of equal voltage rating and 2n-2 neutral point clamped diodes of unequal voltage ratings per leg or per phase. Okay, now figure A shows a phase of 5-level inverter structure. On the other hand, if the diodes of equal voltage rating, each having the same blocking voltage as the switching device, are used, then the more number of diodes have to be connected in series as shown in figure B for 5-level inverters. In this case, the total number of diodes required per pole of the inverter is given by n-1 into n-2, which shows a substantial increment in the diode count. Okay, a pyramid structure of the clamping diode with equal blocking voltage using the same number of diodes as the series connected structure is presented to eliminate the series association of clamping diodes. The quadratic increase in the number of clamping diode leads to the complex power bus structure and make NPC or diode clamped inverter system impractical to implement when the number of levels is sufficiently high. In the multi-level inverter based on neutral point clamp strategy, voltage across the series connected capacitor is assumed to be constant to achieve equal sharing of DC link voltage among the switches. But these capacitor voltage are uh, but these capacitor voltage can fluctuate over a fundamental cycle depending on the load current drawn from the DC link, and this means that devices are called upon to block higher voltage than ideal conditions, where each device has to block only VDC divided by n-1 for n-level inverter. This voltage unbalance problem can be addressed by special PWM control strategy or by replacing the capacitors with separately controlled DC link voltages. The fluctuations in the neutral point clamp voltage or neutral point voltage of 3-level inverter can be reduced by using inner clamped capacitors across the clamping diodes. Okay, so this is what NPC is all about. Okay, now if you want to see the switching table for 5-level NPC structure is like this. Here we are having 5 different levels as we talked about: VDC by 2, VDC by 4, 0, minus VDC by 4, minus VDC by 2. And here are all those switches, 8 switches, S11, S12, S13 to S18. Okay. As I earlier when we are discussing the 5-level inverter, I have told you that all the switches from S11 to S14 are complementary with the switches S15 to S18, which means when S11, S11, S12, S13 and S14 are operating, S15, S16, S17 and S18 will be not operating or not in working state, okay, or opened in nature. Okay, so to achieve the VDC by 2 voltage, the maximum voltage, we have to uh, close all the upper switches. Okay, and to obtain the lowest voltage, which is minus VDC by 2, we have to connect or close all the bottom switches. Okay, and to achieve the mid voltages between the uh, between plus VDC by 2 to minus VDC by 2, we will use different switching states. Okay, to achieve that voltage levels. Okay. Now we will move to another inverter topology, which is flying capacitor topology or FC multi-level inverter structure. Okay. In 1992, this topology was introduced, okay, or the concept of a multi-level communication cell to be used a building block of multi-level inverter. Okay, as the figure shows, the structure of one such multi-level communication cell, which is equivalent to 1 lakh of a 3-level inverter. In this configuration of the capacitor, C11 act as a floating source charged to VDC by 2, and this circuit is called flying capacitor or capacitor clamped inverter. As independent capacitor clamp the device voltage to one capacitor voltage level. The four switches forming this cell are in two pairs. The inner two switches S11 and S12 and S13, S12 and S13 forming one pair, and the outdoor pair is S11 as S14 forming other pair. The switching within each pair must always be complementary state. Okay, as we have discussed earlier, what is complementary operation? The S12 is complementary to S14 and S11 is complementary to S13, which means when S11 is closed, S13 will be open. Okay, it will be not working. It will not allow current to pass through it. Okay. Now, the DC link voltage, the DC link voltage VDC and the voltage on the floating capacitor VDC by 2 ensures that the blocking voltage across each or any switch is VDC by 2. Okay, thus the general concept here is that the capacitor can be kept charged to half of the DC link voltage, and the capacitor voltage can be added or subtracted from the DC link voltage to generate more levels at the output pole of the inverter. The pole voltage VAO can reach VDC by 2 when the upper two switches, which are S11 and S12, are turned on. Okay, which means when these two switches are turned on, when current flows from O point, okay, or we let see the voltage between O and A, this A point shifts to that upper point. From this point it will shift to this point. Now the voltage between O and A will be VDC by 2. Okay, and if we have to achieve minus VDC by 2, what we have to do, we have to just turn on these two switches S13 and S14. So the A point will come to this point and from here to here. Now we will get VAO as minus VDC by 2. Okay. Now the zero level can be attained by two ways. Okay, in this FC 3-level structure, when by S11 and S13 are on, which means this switch S11 and S13 is on, we will get zero voltage. Why? because it is charged with VDC by 2. Okay, now I am coming from here to here, which means I am getting minus VDC by 2. Now once I am getting minus VDC by 2 here and I am having plus VDC by 2 here, which will cancel out each other. It is positive VDC by 2 and it is minus VDC by 2. So the net voltage will be 0. And similarly the other way is by switching on S12 and S14. So when I move from a point to this point and I am going from this point, as it is short, so I have to come from here to here. Okay, so when I go from A to S12 and from S12 to C11, I will observe plus VDC by 2 voltage. Okay, so now from C11 to switch S14. Okay, now from S14 switch I will go to the point below C1 capacitor where I am observing a minus VDC by 2 voltage. Here we are having minus VDC by 2. Earlier we were having VDC by 2. So the net voltage across O and A point is 0. Okay. So we have two switching states for 0 voltage level. Okay. Now the availability of such redundancy of switching combination is realizing the intermediate voltage level is a unique feature of a multi-level inverter configuration based on these cells. Further, this unique feature of switching redundancy associated with a phase can be used as an added advantage to the maintenance of capacitor voltage balancing. The relationship between pole voltage and switching states of the inverter can be summarized in the form of a table as shown on your screen. The multiplicity with or the redundancy with which the mid voltage level are obtained increased for flying capacitor structure of higher levels. For example, for 5-level flying capacitor structure as shown on your screen, the redundancy for the pole voltage levels of VDC by 2, VDC by 4, 0, minus VDC by 4 and minus VDC by 2 are 1, 3, 6, 3, 1 respectively. Okay, in this configuration, also by proper selection of the switching combinations, the capacitor voltage can be maintained at balanced state. Okay. Now this figure gives one leg of a 5-level inverter. The voltage across the floating sources or flying capacitors naturally evolves to the expected value of long loop system or open loop system. Okay, in other system or other systems, these capacitor voltage have to be kept constant by ensuring equal charging and discharging of these capacitors over the switching time period. This is achieved by proper selection of the switching combinations to impose equal duty ratio in the respective switches. Hence, the control strategy employing in flying capacitor flying capacitor based multi-level inverters should be able to maintain the capacitor voltage in addition to the required control action. The fault tolerant design of 4-level flying capacitor inverter with the capacitor voltage balancing is described in many literatures, which provide the same number of levels even in the condition of single switch volt per phase. An extended operation of flying capacitor multi-level inverter by altering the ratio of the capacitor voltage is reported. However, redundant switching states vital to capacitor voltage balancing are sacrificed to achieve higher number of output voltage levels. The flying capacitor multi-level inverter do not need the clamping diodes but need a large number of bulky capacitors as floating source to clamp the voltage. If capacitors with equal voltage rating, which is VDC divided by n minus 1, as the main switch are used, an n-level inverter will need n minus 1 into n minus 2 divided by 2 capacitors per pole as floating source in addition to n minus 1 main DC link or DC bus capacitors. In inverters where a number of level is high, the control also become complicated as the voltage across a large number of capacitors have to be maintained by ensuring proper duty ratio in the switches, but the same amount of energy or voltage storage in the capacitor provide better ride through capability to this class of inverter against the input supply interruptions. Okay, so if we talk about the 5-level inverter of FC topology, okay, here are 1, 2, 3 different floating capacitors providing 3 different voltage levels: VDC by 4, VDC by 2, 3 VDC by 4, and here are 4 different capacitors, which is n minus 1 number of capacitors used as or used for source main supply point. Okay, so if I have to achieve VDC by 2, I have to turn on all the top switches, okay, which are S11, S12, S13 and S14. So when I come from this point A, I will go from S14 to S13 to S12 to S11 to this point, okay, where I will observe the voltage as VDC by 2. Okay, so I will get VDC by 2. So now if I have to get minus VDC by 2, what I have to do, I have to just turn on all the bottom switches. Okay, so I will come from A to S15, then S16, then S17, then S18 to this point, and I will get a voltage of minus VDC by 2 between A and O point. Okay, now if I want to get VDC by 4, then what I have to do, I have to just turn off this S11 and just turn on this S15 switch. Okay, just turn off this S11 and turn on S15, as these are complementary in nature. So as soon as I turn off this, I have to turn on S15. So now I will move from A point to S15, then from S15 I will come to C13, where I will uh, observe a voltage of minus VDC by 4. Okay, now with the voltage of minus VDC by 4, I am moving towards S13 from C13 capacitor. Now from S13 I will go to the point to the switch S12. Okay, from S12 point I will sorry, this is not how it works. It's my fault. as S14 and S15 are complementary in nature. Okay. S14 and S15 are complementary in nature. Okay, so what I will do is I will turn on this S15 and I will turn off this S14. Now I am moving from a point. Okay, when I reach this point, this is short and this is open, so I will move from S15 with, and when I reach to the capacitor C13, I will observe a voltage of minus VDC by 4. Okay, so with the minus VDC by 4 voltage, I am moving towards S13, from S13 to S12, and from S12 to S11. Now from this point, I will get to this point where I am having voltage VDC by 2, and previously I am having voltage minus VDC by 4. So the net voltage will be plus VDC by 4. Okay, this is one method to achieve VDC by 4. Another method is to turn on turn off S11. Okay, and S11 and S18 are complementary in nature. So as soon as I turn off this S11, I will turn on S18. So now what happening is here, we have to do is just moving, we have to just move from a point. Okay, now when I am moving from a point, I will observe that S14 is short and S15 is open. So move up S1 from S14 to S13, then to S12. Okay, now I am at point S12. Okay, and I know the S11 is turned off. So I will move from this point to C11 capacitor. Okay, and now I am observing a 3 VDC by 4 voltage level. Now with this voltage 3 VDC by 4, I am moving towards the switch S18, which is short, and hence I will get to a point where the voltage level is minus VDC by 2. So the net voltage I am observing at this point will be 3 VDC by 4 minus VDC by 2. Hence the net voltage will be VDC by 4. Similarly, I can achieve different levels of voltage from VDC by 2 to VDC by 2 to minus VDC by 4 in steps of VDC by 4. Okay. Now coming to another topology of multi-level inverter, which is Cascaded H bridge. Okay. Now in multi-level inverter structure can be released by cascading or connecting in series several single phase H bridge structures with separate DC source, and this technique have been adopted for high power induction motor drive applications. Okay, here. Okay, as the figure shows, the cascaded multi-level inverter configuration, which consists of two cascaded cells for each phase and result into a 5-level inverter structure. Okay, each cascaded cell full consists of the full bridge inverter fed from an isolated rectifier. The output of each cell is like a 3-level single phase inverter and can attain any of the 3 voltage levels, which is VDC by 2, 0 and minus VDC by 2, depending upon the state of switches. Okay, 2 switches is in each leg from a complementary pair, that is S11 and S14. Okay, in a cell, when switch S11 is and S12 are switched on, which means this one's S11 and S12 is on, the output voltage level is equals to minus VDC by 2, and when S13 and S14 are turned on, the voltage output voltage level is equals to VDC by 2. And when S11 and S13 and or we can say S14 and S12 are turned on, the voltage level of the cell is 0. Thus, depending on the state of switching in the phase A inverter cell, the pole voltage of phase A can be either VDC by 2, 0, minus VDC by 2 or minus VDC. Thus, form a 5-level inverter structure. In general, the number of steps in the output pole voltage for cascaded inverter structure is given by N is equals to 2M plus 1, where M is number of isolated DC supply per phase. Such N minus 1 by 2 H bridge cells, each one having separate DC source of VDC by N minus 1, can be sequentially connected to achieve one leg of N level inverter. Okay, this type of cascaded inverter have been in high power DC application because of their modular structure and and simplicity of control. They are particularly attractive for large electric drive application where separate DC sources are available for large number in form of batteries. The inverter structure in every cell is as each cell or as each inverter cell has identical structure, and thus the extension to higher level does not add any power or more power bus complexity. Also, the compliance like the capacitor voltage balancing or clamping diode slash or clamping diodes or capacitor etc are not required. The limitation of this topology is the requirement of large number of separate DC sources. Okay, but if the DC power supply are supplied through phase shift transformer, every good power quality can be, or sorry, very good power quality can be achieved at the utility side. A scheme of modular motor or modular multi-level inverter is investigated for a medium voltage induction motor drive where two three-phase inverter fed a same motor through the two different set of group of coils of the machine, where uh, the switching state redundancy can be best utilized to equal distribution of switching losses among the various cells. The cascaded inverter, active front end for regenerative capability is also reported in different literatures. Okay, the controlled front end rectifiers for individual cell provides regenerative capability to this configuration. Okay, now if we talk about the 5-level configuration as shown on the screen, this is the configuration where two cells are attached and the cell is shown here. These two cells will give a 5-level output to the induction motor. Okay, so now if I have to achieve the VDC voltage at the output point, okay, or VAO, where A is here and O is here. If I have to achieve VAO, what I have to do, I have to just turn on this S13 and S14 for VDC by 2 from upper one, and similar S13 dash and S14 dash from lower cell to get VDC by 2. Hence, the net voltage will be VDC. Similarly, for minus VDC, I have to turn on S11 and S12 and in lower cell I have to turn on S11 dash and S12 dash. Okay, and in similar manner of switching, I can achieve 5 different levels of voltages, which are VDC, VDC by 2, 0, minus VDC by 2, and minus VDC. Okay. Now here for VDC by 2, I have 1, 2, 3, 4, 4 different switching states. Similarly, for minus VDC by 2, I am having 4 different switching states. While for 0 level, I am having 1, 2, 3, 4, 5, 6 different switching states. Okay, so by switching these different switches in 6 different manners, I can achieve 0 voltage level. Okay. Now let's take one more topology, which is asymmetric DC link voltage cascaded at H bridge multi-level inverter topology. Okay. The multi-level configuration of higher level require large number of components such as clamping diodes, clamping capacitors, and isolated power supplies. In the asymmetric cascaded multi-level configuration, the individual cell can have different ratio of voltage of higher number of levels in the output voltages. If the 5-level topology as shown in figure, the voltage of 2 cascaded inverter cells are chosen in ratio of 2:1. Okay, the voltage of bottom inverter is equals to VDC by 3, and that of top inverter is 2 VDC by 3. Okay, then the same circuit configuration can give 7-level inverter structure. Okay, the pole voltage VAO can have 7 levels, which are VDC 2 VDC by 3, VDC by 3, 0, minus VDC by 3, minus 2 VDC by 3, and minus VDC. Okay. Now the advantage of such multi-level topology is the requirement of minimal number of devices as proposed in the literature. It is possible to operate the inverter at different frequencies, and in extreme case, the top inverter can switch the fundamental frequency and the bottom inverter can be switched at PWM frequency, switching frequency, to improve the overall efficiency of the drive. Hence, the switches in the top inverter can be replaced by low frequency, high voltage GTO devices, and while the bottom inverter can be normal IGBT inverters. Okay, therefore the inverter is called hybrid multi-level inverters. In the configuration using such asymmetric DC source, the stress on the device will be unequal and will depend on the DC source, with devices at higher end requiring to block large voltages. This way, by cascading the number of H bridge inverters, H bridge inverters, there are with their DC voltages varying in binary weighted fashion from VDC divided by 2 to the power m minus 1 to 2 to the power m minus 1 VDC by 2 to the power m minus 1. Okay, one can achieve 2 to the power m plus 1 minus 1 levels of inverter output. Other configuration of cascaded inverter structure can also be investigated from also be investigated for induction motor applications. Okay, mixed level hybrid multi-level structures can be realized by a single phase H bridge multi-level H bridge cell. Okay, series combination of 3-phase 6-switch VSI or voltage source inverter with single phase H bridge is proposed to release energy sufficient asymmetric hybrid cascaded multi-level inverter. Okay. Now, cascaded conventional two-level inverters. Now, multi-level inverters scheme is a multi-level inverter scheme is presented by cascading uh, two-level inverters as shown in figure. This inverter configuration generates a three-level output voltage at the pole of bottom two-level inverters. Okay, this three-level inverter can also be used as a two-level inverter in lower speed range over clamping one of the two level inverters. Okay, the considerable advantage here is the absence of the clamping diodes as required in three-level NPC inverter, and the inverter power bus structure very simple as conventional two-level DC, two-level structure is retained. Okay, in this configuration, the switching device in one leg of the individual two-level inverter are always switched in complementary fashion, provided the capacitor voltage are equals to half of the DC link voltage, which is VDC by 2. Then the voltage VA2O, VA2O, or we can say VOA2 can be either VDC by 2, 0 or minus VDC by 2. Okay, as shown in the table. It can be seen from the figure as the voltage rating of the bottom switch in the leg has to withstand full DC link voltage. This switches S22, S24, S26 has to be rated for VDC voltage. Okay, even though the bottom switches or bottom devices have to block full DC link voltage, this scheme is attractive for medium voltage drive applications because of modular nature and modular structure. Okay, so this is and these are all different kind of multi-level topologies. Okay, in next lecture of this series we will see another topology for multi-level inverter, which is dual induction motor, dual fed induction motor topology. Okay, in that we will see a multi-level inverter topology with dual inverter fed open and winding induction motor. Okay, so please see that video to get get the knowledge of every topology, including conventional and advanced ones. Thank you.